Over the last little while, we've covered the entirety of forces and fields. We've looked at Coulomb's law, we've looked at electric fields for point charges, electric fields for parallel plates, we've looked at many different configurations with magnetic fields. And at this point in your high school physics career, you've covered the three major fields we talk about. We did gravitational fields in Physics 20, and then in this unit, we've talked about electric and magnetic fields. What we want to do is we want to make a little bit of comparison between the fields. We want to talk about things that are similar, we want to talk about some differences. This is a very common question on a diploma exam, ask you to compare fields. Could be a multiple choice question. This is one of those cases where they really like to make use of that Venn diagram. And you can find that in one of the released examples. So like a Venn diagram with all three fields, and then it'll give you some statements about the fields, and you have to say, does it apply to like the electric field, does it apply to electric and gravitational, electric, magnetic, all the fields, etc., etc. So it looks at all possibilities. So let's have a look at electric and magnetic fields. So when we're talking about electric fields, what we're really talking about is the electric field between point charges, or Coulomb's law. And when we're talking about gravitational fields, we're talking about Newton's law of universal gravitation. And then for magnetic fields, we have two choices. We have QVB or we have ILB. Again, depends on the situation. Now, some of these similarities and differences, you may be able to argue different points. Like the answers here can be a little bit fluid. I'm just looking at kind of the major points where they'd be trying to hit on in terms of the diploma, like what they're going to be most likely asking about. So with electric and magnetic fields, the big similarity between the two of them is that they can both be attractive and they can be repulsive. So electric fields can be attractive if you have opposite charges. They can be repulsive if you have like charges. And then magnetic fields, if you have like poles, they're repulsive. If you have unlike poles, they're going to attract. So they can both be attractive and repulsive. In terms of differences, like I said, you could really play around with semantics on this one. You know, if you want to give the real technical answer, you could say, well, electric fields deal with, electric force, magnetic fields deal with magnetic force. And fair enough, you're technically not wrong about that. The big one that they're looking for is they're going to say Fe varies as 1 over r squared. So it's got that 1 over r squared relationship, Coulomb's law. But Fm does not vary as 1 over r squared. That's the big one they're looking for there. How Fm varies? Magnetic fields, for those of you that study physics a little bit on high school, you're going to find that magnetism can get really complicated, so I don't want to overstep my bounds on this one. We'll just leave it at that. In terms of electric and gravitational fields, this is a big thing we always talk about with Coulomb's law. So here's Coulomb's law, Newton's law of universal gravitation. So the big thing that's going to stick out is they both vary as 1 over r squared. So they have that inverse square relationship. As I've mentioned earlier, inverse square relationships are quite common in physics. The other thing with electric and gravitational fields is they both have attractive properties, or they can both be attractive. So gravitational forces are always attractive. They're always trying to bring masses together. As mentioned previously, electric fields, they can be attractive when you have unlike charges. The big difference between these that the diploma would be sort of aiming for, the big difference is that electric fields can also be repulsive, but gravitational fields cannot be. So Fe can be repulsive, but Fg can only be attractive. And then the last kind of paired combinations, we're looking at gravitational and magnetic fields. The only real thing that we can say, kind of the similarities with electric and magnetic fields, almost, we can just say gravitational and magnetic fields, they can both be attractive. And honestly, that's really all you're going to be able to say for that. And in terms of differences, there's kind of two things we can put. Again, Fg varies as 1 over r squared. Fm does not do that. And then we also know that the magnetic force can be repulsive, but the force of gravity is strictly an attractive force. So there's two things we could really put here if we want. So Fm can be repulsive, but Fg can only be attractive. And then, as I said, Fg varies as 1 over r squared, but Fm does not. Should make these blanks a little bigger. I'll have to note that for next time. As I said, when you're talking about similarities and differences, you can really stretch it out here. Like I said, you could say, well, gravitational force deals with gravitational fields and magnetic forces deal with magnetic fields. That's a difference. Well, you are technically correct. That's not wrong. But most likely that's not what the diploma is aiming for. The last big one, and this seems to get asked frequently on the diploma, what is similar between all three of these fields? Like, what is a property that they all share? And you've probably been told this already, or you may have noticed this as we go through the similarities and differences. All three fields can be attractive. Gravitational fields can be attractive, magnetic fields can be attractive, and electric fields can be attractive. And this is the big one they're looking for. Whether you see that on a diploma, honestly, it'll just depend on the year, but that's certainly the big one. And the very last thing we just got to touch on very quickly here is test objects. So as we've mentioned, fields are not a real thing in the sense you can't go outside and be like, oh, there's the gravitational field, oh, there's the electric field, like you can see it. All you can see is the effect on the object. So you can see the effects of gravitational fields on objects, like anything with mass, or electric fields on charged particles. The field theory is basically our mathematical description of the observations that we have noted. And of course, over time, as more evidence has been gathered, we've refined those fields. But in order to actually test for the fields or see whether they're present, we have what are called test objects. Like, this is what we use to determine whether the field is present or not. So in high school, as we mentioned, the three big fields we look at are gravitational fields, electric fields, and magnetic fields. So for a gravitational field, the test object is literally anything with mass. So any object with mass will do. So this pen I'm writing with, that'll work. The note package, your computer, you yourself, all those things are great for testing gravitational fields. When we talked about electric fields, the definition that we use for an electric field to test for it is a small positive test charge. Because then what we do is we ask ourselves the question, okay, in this situation, where would a small positive test charge want to go in response to the source charge? Where that positive test charge goes, that is where we're going to have the direction of the electric field. And the last thing is the magnetic field. For a magnetic field, our test object is the navigator's best friend. We're just going to use a compass. Where the north needle of the compass points, the north needle is telling you the direction of the magnetic field at that point. And that wraps up forces and fields.